Designing with events, domain modeling and patterns for event sourcing. 1. The case for event sourcing. Beyond CRUD, every software application, at its core, exists to manage information. From the simplest to the most complex, systems are built to store data, retrieve it, present it to users, and allow them to modify it. For decades, the dominant paradigm for achieving this has been what's commonly known as CRUD, an acronym representing the 4 fundamental operations: create, read, update, and delete. This model, often implemented directly on top of relational databases, feels intuitive and straightforward. A new user signs up. Create a user record. They log in, read their record. Their email address changes, update the email field. They decide to leave, delete their record. For many applications, particularly those focused on managing static, independent pieces of information, CRUD-based systems are simple, efficient, and perfectly adequate. They align well with the way we often perceive data, as a collection of current states. However, as applications grow in complexity, as business rules evolve, and as the demand for deeper insights into user behavior intensifies, the limitations of the CRUD paradigm begin to emerge, often painfully. The simplicity that makes CRUD appealing for basic scenarios becomes its Achilles heel when faced with the dynamic, historical, and interconnected nature of real-world business processes. Consider a simple order management system built on CRUD. When a customer places an order record is created. When the customer updates their shipping address, the shipping address field in that order record is updated. If an item is canceled, the status might be updated to canceled, or perhaps the item is even deleted from the order line items. What's lost in this typical CRUD approach? History. We know the order is currently shipped, but how exactly did it reach that state? Was it first placed, then processed, then packaged, then shipped? Or did it go from placed to canceled and then somehow get reopened and shipped? The traditional database only tells us the current state. The rich narrative of how that state came to be, the exact sequence of events, is overwritten and forgotten with each update or delete operation. This fundamental loss of history creates several significant challenges. Auditing becomes an afterthought. Many complex applications, especially in finance, healthcare, or logistics, require a comprehensive audit trail. Who did what, when, and why? In a CRUD system, this often leads to the cumbersome practice of manually adding history tables or log entries, triggered by database events or application logic. These audit trails are often imperfect, prone to missing details, separated from the core business logic, and difficult to query meaningfully. They are a bolt-on solution to a problem that CRUD doesn't inherently solve. Understanding how we got here is difficult. When a customer calls with a complaint about an order, a support agent might need to understand every step of that order's journey. Why was it delayed? When exactly did the address change? If the system only stores the current state, answering these questions involves piecing together fragments from scattered log files, email trails, or even human memory, which is inefficient and error-prone. Complex business logic and state transitions. Business processes are rarely simple state machines with clear, unidirectional transitions. An order might be placed, then pending payment, then paid, then shipped. But what if a payment fails? The order might go back to pending payment or into a payment failed state. Business rules often depend on past states or sequences of events. Trying to manage this intricate dance of updates, and if-then logic on a current state model can lead to a big ball of mud architecture, where adding new features or changing existing ones carries high risk. Limited business intelligence and analytics. Imagine a marketing team wants to understand customer behavior. Was it common for users to add an item to their cart, then remove it, and then add it back? Or did they just add it once and proceed? With only current state, such questions are hard, if not impossible, to answer without extensive and costly data warehousing efforts that try to reconstruct the past. Challenges in debugging and error recovery. When something goes wrong, debugging becomes challenging. If we only have the end state, how do we recreate the exact sequence of operations that led to the error? In production, if data becomes corrupted, restoring it conventionally often means rolling back to a previous backup, which loses all legitimate changes made since that backup. At its heart, the limitation of CRUD is that it focuses on what the system looks like now, at the expense of how it got there. It treats data as a static snapshot, while the reality of business is a dynamic, continuous flow of discrete actions. This is the core problem that event sourcing aims to solve. Instead of storing the current state of an application's data, event sourcing fundamentally changes the way we persist information. Imagine your system is not just reading and writing to a database, but rather acting as a meticulous historian, recording every significant action as an undeniable, immutable fact. In event sourcing, the system's source of truth isn't its current state in a traditional database table. Instead, it's a sequence of events, an append-only log of everything that has ever happened within the system. Think of it like a financial ledger. A bank doesn't just store your current balance. It stores every single transaction, every deposit, withdrawal, transfer that led to that balance. Your current balance is merely a calculated projection derived from that immutable log of transactions. Similarly, in event sourcing, every change to the application state is captured as an event. An event is a past tense statement that describes something that has already happened. Order placed, item added to cart, payment received, shipping address changed. Once an event has occurred and is recorded, it can never be changed or deleted. It's a permanent record of a fact. To determine the current state of any entity, like an order or customer, an event source system doesn't query a database for a row that holds the current values. Instead, it reconstructs that state by replaying the relevant stream of events, applying each event in chronological order, from creation to the present moment. This shift in perspective, from storing state to storing events, offers profound benefits and addresses the exact limitations that CRUD systems encounter when facing complexity. Complete an inherent audit trail. Every change that ever happened is recorded as an event, providing a perfect, built-in audit log. This is not an add-on, it is the fundamental data model. Unparalleled business insight. Because all historical events are preserved, businesses can ask questions that are impossible with current state models. How many users clicked Add to Cart but never checked out? What was the average time between an order being placed and being shipped last year? The event stream becomes a rich source for analytics, business intelligence, and machine learning. Temporal queries and time travel. Need to see what an order looked like last Tuesday at 3 p.m. Simply replay the events up to that point in time. This capability is invaluable for debugging, compliance, and even rerunning past scenarios to understand business decisions. Simplified state evolution. As business requirements change, you don't necessarily have to migrate all your existing data. You can often simply create new consumers, projections, of the historical event stream, reinterpreting past events to generate new views or states without altering the original facts. Robustness and error recovery. If an error occurs that corrupts a calculated state, you can simply discard the corrupted state and recreate it perfectly by replaying the events. Events are the true source of truth, making data loss extremely difficult. Natural alignment with event-driven architectures. Events are inherently suitable for communication between different services or components within a distributed system. As one service generates an event, other services can subscribe to it and react accordingly, fostering loose coupling and greater scalability. Decoupling of write and read models, CQRS. Event sourcing naturally pairs with Command-Query Responsibility Segregation, CQRS. Writes operate on the authoritative event stream to produce events, while reads query highly optimized read models, or projections, that are built from those very same events. This allows read concerns and write concerns to scale and evolve independently. Event sourcing is not a silver bullet, and it introduces its own set of considerations, such as eventual consistency for read models and the complexities of event versioning. However, for systems that demand high auditability, deep historical insight, robust error recovery, and the ability to adapt to complex, evolving business processes, it provides a powerful, elegant, and surprisingly intuitive architectural foundation. This book will guide you through the principles of domain modeling and the design patterns necessary to unlock the full potential of event sourcing, empowering you to build resilient, scalable, and insightful software systems that truly reflect the dynamic nature of your business. We will begin by exploring the foundational concepts that make event sourcing tick. 2 core concepts of event sourcing. In the previous chapter, we introduced event sourcing as a paradigm shift from storing current state to storing a chronological log of events. To truly grasp its power and implications, it's essential to understand the fundamental building blocks that constitute an event source system. These concepts are not just abstract ideas. They are the concrete components you will design and implement. Let's define these core terms: events, event stream, aggregate, and event store. We'll also introduce the concept of projections or read models, which become crucial when querying our event-driven system. Events, the immutable facts. At the heart of event sourcing is the event. An event is an immutable past tense statement that describes something significant that occurred within your domain. It's a record of a fact. Immutable. Once an event is recorded, it can never be changed or deleted. This immutability is fundamental to event sourcing's power. If a fact changes, it means a new event occurred to signify that change, not that a past fact was rewritten. Past tense. Events describe what has already happened, not what should happen, which is a command, or what the current state is. Examples include customer registered, order placed, item added to cart, shipping address changed, payment failed. Business-centric. Events should reflect business occurrences, not technical implementation details. While a database record updated event might describe what happened technically, a product name changed event describes the business reality. Self-contained. An event should contain all the necessary data to describe that specific occurrence at that point in time. For a customer-registered event, this might include the customer's ID, name, email, and the registration timestamp. It doesn't need to describe the entire customer object, just what relates to that specific happening. Consider the example of a simple user entity. In a CRUD system, updating a user's email might change a field in a user's table. In an event source system, it's a user email updated event, which contains the user ID, the old email address, and the new email address. The old email address being part of the event is crucial. It confirms the event occurred when the user had that specific old email address. Why are events so powerful? They represent the true, unchallengeable history of your system. They capture intent and causality. This makes auditing simple, debugging precise, and replayable for various purposes. Event stream. The chronicle of an entity. An event stream is a logically ordered, chronological sequence of events pertaining to a single entity or aggregate. Think of it as a personal diary or ledger for one specific item in your system. For our user example, the event stream for a user with ID user 123 might look like this. Customer registered, user ID. User 123 name, Jane Doe, email, jane@example.com. Shipping address added, user ID. User 123 address, 123 Main Cent City, any town. User email updated, user ID. User 123, old email, jane@example.com new email, janedoe@example.com. Password hash changed, user ID, user 123. Each event in the stream has a unique identifier and an increasing version number, or sequence number, within that stream. This version number is vital for ensuring correct ordering and detecting concurrency issues. The order of events within a stream is paramount. It defines the history. The event stream for one aggregate is independent of another. An order aggregate will have its own stream, order placed, item added, payment received, order shipped, distinct from a customer aggregate. Aggregate, the consistency boundary. In the context of domain-driven design, DDD, an aggregate represents a cluster of domain objects that are treated as a single unit for data changes. It is a transactional consistency boundary. In event sourcing, the aggregate takes on an even more crucial role. It's the entity around which your event stream revolves. When you want to make a change to a piece of data within your system, you effectively issue a command against an aggregate. The aggregate then decides whether to accept that command based on its current state, which it reconstructs from its event stream and its business rules. If the command is accepted, the aggregate produces one or more new events, applies them to itself to update its state, and then persists these new events to its event stream. Let's revisit our order example. The order itself is an aggregate. A place order command would be sent to an order aggregate or a factory to create one. The order aggregate would validate the command, e.g., are items in stock. If valid, it would produce an order placed event and perhaps order item added events for each item. These events are applied to the order aggregate's internal state and then saved. The aggregate acts as a protector of its invariants, the business rules that must always be true for that aggregate. Any operation that would violate these invariants must be rejected. All changes to an aggregate must go through the aggregate route. This ensures that the state of your service as determined by the aggregate is always consistent according to its business rules. A key aspect of event sourcing with aggregates is that changes are applied as events. The aggregate loads its past events, applies them one by one to recreate its current state in memory, then processes the new command, generates new events, and finally saves these new events. This process is often called rehydrating the aggregate. Event store, the immutable database. The event store is the specialized database or persistence mechanism designed to store your event streams. Unlike traditional databases that store the current state of entities, the event store stores the ordered, immutable sequence of events for each aggregate. Key characteristics of an event store: append only. Events are only ever added, they are never updated or deleted. This aligns with the immutability principle. Version streams. It supports storing events in version streams, typically one stream per aggregate. This ensures that when you read an event stream, you get all events in the correct chronological order, with identifiable versions. Optimized for writes. Event stores are optimized for high-volume appends. Idempotency, often built-in support. The ability to handle duplicate commands without leading to duplicate events, or duplicate events without leading to duplicate state changes. Subscription mechanism. Many event stores offer a mechanism to subscribe to new events as they are appended, enabling a reactive architecture where other parts of the system can react to changes. The event store is your primary source of truth. If you lose all your read models, you can always rebuild them from the event store. If your application crashes, you can recover its state by replaying events from the event store. Projections/read models. The queryable views. While the event store is excellent for writing and retrieving event streams, it's not designed for direct querying of the current state of your data. Asking, what is the total order value for customer X? Or, find all unpaid invoices for customer Y becomes challenging when your data is spread across many event streams. This is where projections, often called read models or materialized views, come into play. A projection is a denormalized, query-optimized view of your data, built by consuming events from the event store. When a new event occurs, e.g., order placed, item added to order, payment received, your application can process this event and update one or more projections. Consider our order example. An order placed event comes in. A current orders projection might insert a new record for this order, an item added to order event. The current orders projection updates the total price of that order, an order shipped event. The current orders projection might remove the order or mark it as shipped. A separate customer order history projection might just append the order ID to a list associated with the customer whenever an order placed event occurs. Key aspects of projections. Optimized for reads, they are designed for efficient querying, often using traditional relational databases, NoSQL databases, or search engines. Eventually consistent. Since projections are built by processing events, there's a small lag between an event being recorded in the event store and the projection being updated. This means projections are eventually consistent with the event store. For most user-facing queries, this tiny delay is acceptable. Disposable and rebuildable. Because projections are derived from the immutable event store, you can delete and rebuild them at any time by replaying all historical events from the event store. This is incredibly powerful for schema migrations, bug fixes in your projection logic, or creating new views of your data. Tailored to query needs, you can have multiple projections for the same event stream, each optimized for a specific query or UI screen. This is a core tenet of Command-Query Responsibility Segregation, CQRS, which naturally complements event sourcing. The flow, from command to projection. Let's put these concepts together with a typical flow in an event source system. A command, e.g., place order command, comes into the system, triggered by a user interface or another service. The command encapsulates the user's intent. The command is routed to the appropriate aggregate, e.g., the order aggregate. The aggregate loads its current state by replaying its event stream from the event store. The aggregate processes the command, validates it against its current state and business rules. If valid, the aggregate produces one or more new events, e.g., order placed, payment initiated. These new events are then appended to the aggregate's event stream within the event store. This is the transactional boundary. Once the events are successfully persisted, they can be published. Event handlers or subscribers, often within different microservices or parts of the same service, consume these new events. These event handlers then update one or more projections read models, e.g., an open orders list, a customer dashboard view based on the event's content. This continuous flow from command to event to event store, event to projection, forms the backbone of an event source system. It creates a robust, highly auditable, and incredibly flexible architecture capable of evolving with your business needs. In the next chapter, we will delve deeper into domain-driven design, which provides the crucial modeling discipline necessary to define these events and aggregates effectively. 3 Domain-driven design fundamentals. The foundation for event sourcing. While event sourcing provides a powerful architectural pattern for persisting data and managing state, it doesn't tell you what data to persist or how to organize your application's logic. This is where domain-driven design, DDD, becomes not just complementary, but foundational. Event sourcing thrives when built upon a strong understanding and application of DDD principles. Without a well-modeled domain, your event streams risk becoming a chaotic log of technical changes rather than a meaningful business narrative. DDD, as championed by Eric Evans in his seminal work, Domain-Driven Design, Tackling Complexity in the Heart of Software, is an approach to software development that focuses on connecting the implementation to an evolving model of the core business domain. It emphasizes collaborative understanding between domain experts and software developers, fostering a shared language and clear boundaries. Let's explore the key DDD concepts that are particularly relevant to event sourcing. Ubiquitous language, speaking the business language. At the very core of DDD is the concept of the ubiquitous language. This is a shared language that all team members, developers, testers, business analysts, and domain experts use consistently to discuss the business domain and the software system. It's not just a glossary of terms. It's a living, evolving vocabulary used in conversations, documentation, and most importantly, directly within the code, class names, method names, variable names, and event names. Why is this crucial for event sourcing? Clarity of events. If your events are to reflect business facts, their names and data must come directly from the ubiquitous language. An event named order shipped is far more valuable and understandable than process complete or record status updated. The attributes within order shipped should also use terms understood by the business, like tracking number or carrier name. Reduced ambiguity. When everyone uses the same terms for the same concepts, misunderstandings decrease, leading to more accurate models and fewer bugs. Enhanced communication. Discussions about system behavior become more efficient when developers can directly translate business requirements into code constructs and vice versa, using the same language. Model alignment. The ubiquitous language forces the domain model, and thus your aggregates and events, to align closely with the real-world business processes. Example: if the business universally refers to the process of a customer returning an item as a return authorization, then your events should reflect this. Return authorization created, return authorization approved, return authorization closed. Avoid jargon or technical terms that don't originate from the domain. Bounded contexts. Defining logical boundaries. In large, complex business domains, it's common for the same term to have different meanings depending on the context. For example, a product in a sales context might refer to an item for sale with price and availability, while a product in a manufacturing context might refer to its bill of materials and production schedule. Trying to force a single, monolithic model for product across all these disparate meanings leads to a convoluted and difficult-to-maintain system. Bounded contexts provide a solution by defining clear linguistic and model boundaries. Each bounded context encompasses a specific part of the overall domain where a particular model and its ubiquitous language are consistent. Outside that context, the terms might have different meanings, or the model might be different. How do bounded contexts relate to event sourcing? Microservices alignment. Bounded contexts are often a strong indicator for where to draw microservice boundaries. Each bounded context can correspond to a separate microservice, encapsulating its own domain model, aggregates, and event streams. Event ownership. Events are typically owned by the bounded context in which they originate. An order-placed event might originate in an ordering bounded context. Other bounded contexts, e.g., shipping, inventory, billing, might subscribe to this event and react to it, but they don't own it or produce it. Simplified models. Within a bounded context, the model remains coherent and focused on its specific responsibilities, preventing the creation of an overly complex, all-encompassing enterprise model. Decoupling. Bounded contexts promote loose coupling between different parts of a large system. They interact through well-defined interfaces, often by publishing and subscribing to events. This is critical for scaling and managing complexity. Identifying bounded contexts is a crucial step in designing any large system, and particularly an event-sourced one. Tools like event storming, which we'll discuss in Chapter 5, are excellent for this. Entities and value objects, building blocks of the domain. Within a bounded context, the domain model is built using specific types of objects. Entities. An entity is an object defined by its identity and continuity over time, rather than its attributes. Even if its attributes change, it's still the same entity. Examples include customer, order, product. An order has an orderid that uniquely identifies it regardless of its status or line items. In event sourcing, entities are often the core of your aggregates. Value objects. A value object is an object that primarily describes a characteristic or attribute. It has no conceptual identity. It is immutable, and its identity is determined by the combination of its attribute values. If you replace one address value object with another, you're not changing the same address. You're replacing it with a new one. Examples include address, money, date range. Value objects are often deeply embedded within entities or events, providing rich, type-safe data. In event sourcing, events often carry value objects as part of their payload, e.g., an order-placed event might include a money value object for the total amount and an address value object for the shipping address. The concepts encapsulated by entities typically become your aggregates, around which event streams are built. Aggregates, consistency guardians in DDD. We briefly introduced aggregates in Chapter 2, but their conceptual origin lies firmly within DDD. In DDD, an aggregate is a cluster of associated objects, entities, and value objects that are treated as a single unit or transactional consistency boundary. One of the objects in the cluster is the aggregate root, and it's the only object that external clients can hold references to. All operations on the aggregate must go through the aggregate root. The purpose of an aggregate is to protect its internal invariants, rules that must always be true. For example, an order aggregate must ensure that its total amount calculation correctly reflects its line items. You don't update an order item outside the order aggregate. You send a command to the order aggregate to add item to order or remove item from order. In event sourcing, each aggregate corresponds to an event stream. The events within that stream are the changes specifically pertaining to that aggregate. The aggregate root is responsible for deciding which events to produce when a command is received, based on its current state, reconstructed from its event stream, and its internal business rules. The aggregate state is built by applying its sequence of past events. This means the aggregate's internal logic is purely additive. It takes a command, generates new events, and applies them. It doesn't perform updates in the traditional sense. Example, an order aggregate might contain order items entities and a shipping address value object. The order itself is the aggregate root. When a change shipping address command arrives, the order aggregate validates it and emits shipping address changed event. When an add line item command arrives, the order aggregate validates it and emits an line item added event. This strict adherence to the aggregate boundary is crucial for maintaining data consistency in event source systems, especially in distributed environments. Tactical versus strategic design. DDD distinguishes between two levels of design. Strategic design. This focuses on the high-level organization of the domain, identifying ubiquitous language, bounded contexts, and the core domain. It's about drawing the big picture. Tactical design. This deals with the details within a bounded context, such as designing aggregates, entities, value objects, domain services, and repositories. It's about designing the specific components that implement the domain model. When approaching event sourcing, strategic design guides you in defining your microservice boundaries, corresponding to bounded contexts, and identifying the major business events that flow between them. This shapes the overall event topology. Tactical design guides you in defining the specific aggregates within each microservice and the granular events those aggregates produce and consume. This ensures that your aggregate boundaries are correct and that your events are meaningful single facts. The synergy, DDD as a guiding light for event sourcing. The synergy between DDD and event sourcing is profound. DDD provides the intellectual tools and practices to model complex business domains effectively, leading to domain models that are clearer through ubiquitous language, maintainable through bounded contexts, consistent through aggregates, expressive through entities and value objects. Event sourcing, in turn, provides a persistence mechanism that perfectly aligns with these DDD principles. By storing the domain's narrative as a sequence of immutable events, it inherently supports temporal modeling, capturing the evolution of entities over time, which often aligns with business processes. Event-driven communication. Events are a natural way for bounded contexts to communicate without tight coupling. High fidelity. Your system's history truly reflects the business history. Without a strong foundation in DDD, you risk designing event source systems that are technically correct but business agnostic, ultimately failing to deliver on the promise of deep business insight and adaptability. The next chapter will explore this bridge between DDD and event sourcing, showing how domain events, a DDD concept, transition into the persisted events of event sourcing. 4. Bridging the gap. Domain events and event sourcing. In the previous chapter, we established that domain-driven design, DDD, provides the essential modeling discipline for complex software systems, equipping us with tools like the ubiquitous language, bounded contexts, and aggregates. Now, we'll delve into a specific DDD concept, domain events, and reveal how they form a natural, powerful bridge to the technical implementation of event sourcing. Understanding this connection is crucial, as it elevates your event sourcing efforts from mere technical persistence to a truly business-driven architectural approach. What are domain events in DDD? In DDD, a domain event is a past tense statement that describes something that happened in the domain that the domain experts care about. It's a way to capture significant occurrences within a bounded context. A key characteristic of a DDD domain event is that it's immutable. Once it has happened, it cannot be undone. The primary purpose of DDD domain events is to signal changes that might trigger side effects or reactions within the same or other bounded contexts. For example, in an ordering bounded context, an order-placed event might need to trigger inventory deduction in an inventory bounded context. An order-shipped event might trigger an email notification in a notification bounded context. Within the same bounded context, an account-credited event might trigger a loyalty points awarded action. Traditionally, DDD domain events are often ephemeral. They are raised by an aggregate, handled by one or more subscribers, and then they disappear. They serve primarily as a communication mechanism to decouple parts of your system and manage side effects. The focus has historically been on their role in signaling reactions, not necessarily on their persistence as the primary form of state. From ephemeral domain events to persisted event sourcing events, here's where the bridge becomes clear. The events we discussed in Chapter 2 as the immutable facts persisted by an event store are, in essence, persisted domain events. The order-placed event that was an in-memory communication signal in traditional DDD becomes the order-placed event that is written to the event store in an event source system. The very same event that triggers a side effect can also be the event that constitutes the change to an aggregate state and is stored as part of its historical record. This convergence means that with event sourcing, your ubiquitous language not only defines your in-memory objects, but also directly shapes your persistent data model. The events your domain experts use to describe the business processes are the very events that drive your application state. Let's illustrate with an example. Scenario: placing an order. Command: a user sends a place order command to the system, requesting to order a list of items. Aggregate: the order aggregate within its bounded context receives this command. Validation and decision: the order aggregate performs validations, e.g., are items available, is user authorized. If everything is valid, it decides to accept the order. Domain event generation: instead of just updating internal fields directly, the order aggregate raises one or more new domain events. In this case, an order-placed event might be generated, containing all relevant details like orderid, customerid, order items, total amount, etc. State application: the order aggregate then applies this order-placed event to its internal state. This is how the aggregate updates its own representation of what happened. Persistence, event sourcing. Crucially, this order-placed event is persisted to the event store as part of the order aggregate's event stream. This step is atomic. Either all generated events are saved, or none are. This ensures consistency. Publication for side effects. Once successfully persisted, the order-placed event is then published, e.g., to a message broker. Event consumers: other services or components, e.g., inventory, shipping, billing, notification, subscribe to order-placed events. The inventory service consumes the event and deducts stock, perhaps omitting an items reserved event. The shipping service consumes the event and prepares for shipment. The notification service consumes the event and sends a confirmation email to the customer. In this flow, the order-placed event serves dual purposes. It is the building block of the order aggregate's history, its state evolution, and the message that coordinates activities across the broader system. Why a strong domain model is crucial for effective event sourcing. The seamless integration of DDD domain events with event sourcing highlights why a robust domain model is not merely beneficial, but genuinely critical for successful event sourcing implementation. Meaningful events. Without a clear, ubiquitous language and well-defined aggregates, your events risk being generic, low-level, or technically focused. Entity updated event or data changed event are unhelpful events that tell you something happened, but not what business fact occurred. A strong domain model ensures your events are rich, self-describing, and directly reflect business operations and decisions. Correct aggregates and consistency boundaries. DDD's aggregate pattern helps you define the transactional boundaries for your events. If your aggregates are poorly designed, too large, too small, or protecting the wrong invariants, you'll struggle with consistency issues, concurrency problems, or overly chatty event streams. A well-defined aggregate ensures that events are grouped logically and that atomicity is maintained where it matters most, within the aggregate's consistency boundary. Clear event flow. DDD's emphasis on bounded contexts helps you understand the natural flow of events. Which context emits which event? Which contexts are interested in that event? This clarity prevents a chaotic event soup where events are published indiscriminately, leading to tight coupling and spaghetti logic. Business buy-in and collaboration. DDD encourages close collaboration with domain experts. When events are named and structured according to the ubiquitous language, domain experts can review and understand the event payloads, validating that the system's behavior aligns with their business understanding. This collaborative effort makes the entire system more trustworthy and resilient to change. Evolvability and adaptability. A good domain model anticipates change. When new business requirements emerge, a well-factored system, built with clear aggregates and meaningful events, is far easier to evolve. You can often simply add new events or new event consumers without significantly altering existing code, as opposed to refactoring intertwined current state logic. A pitfall to avoid: anemic events. Just as there are anemic domain models, where business logic resides outside the domain objects, usually in service layers, there can be anemic events. These are events that are technically correct but lacking in business meaning or completeness. For example, an order updated event that simply says order updated without conveying what was updated, e.g., shipping address changed, item removed, etc., forces consumers to query the current state to understand the change, undermining the benefits of event sourcing. A strong DDD practice helps ensure events are expressive, self-contained, and encapsulate a single business fact. In summary, event sourcing is a pattern for persistence and state management, but DDD provides the intellectual framework for what to persist and how to organize it. The domain events of DDD become the very fabric of your event source system, providing a durable, auditable, and highly expressive record of your business's evolution. By deeply understanding your domain and crafting rich, meaningful events and their associated aggregates, you lay the groundwork for an event source system that is not just technically sound, but truly aligned with the needs and narrative of your business. With this foundational understanding, we can now move on to the practical art of modeling these crucial events. 5. Event modeling. Crafting the language of chain. Having established the profound synergy between domain-driven design and event sourcing, the most critical skill to develop is event modeling. This is the art and science of identifying, naming, and structuring the events that will form the immutable backbone of your system's history. Effective event modeling transforms raw data changes into a rich narrative of business facts, making your system auditable, understandable, and adaptable. Poor event modeling, conversely, can lead to ambiguous event streams, difficult debugging, tangled logic due to unclear boundaries, and ultimately undermine the benefits of event sourcing. Techniques for identifying and naming events. The process of discovering and naming events is inherently collaborative and domain-driven. It requires active participation from domain experts and is best done with visual, interactive techniques. 1. Event storming. Event storming is a highly effective, workshop-based technique for quickly mapping out a complex business domain and discovering its events, commands, aggregates, and read models. Developed by Alberto Brandolini, it uses visual tools, sticky notes, large wall whiteboard to bring together domain experts and technical team members. How it works, simplified. Materials. A large, continuous modeling surface, e.g., paper roll on a wall, plenty of orange sticky notes for events, blue commands, yellow aggregates, green read models, pink external systems, etc. The flow. The workshop typically starts by focusing on a specific business process or pain point. Step 1. Discover events, orange. Participants write down every significant change or fact that happens in the business, expressing them as past tense statements. These are put on the wall in chronological order. Example: order placed, payment received, item shipped. Step 2. Identify commands, blue. For each event, participants identify the command that caused it. Commands are user intentions. Example: place order command leads to order placed event. Step 3. Find aggregates, yellow. Group events and commands around the entity that they apply to, identifying aggregates. These are the consistency boundaries. Example: order aggregate processes place order and emits order placed. Step 4. Identify read models, green. Discover what data structures are needed for users to query the system or make decisions. Example: order details view to display information about an order. Step 5. External systems, pink. Identify any external systems that produce or consume events. Benefits: shared understanding. Forces collaboration and builds a shared ubiquitous language. Rapid discovery. Can map out complex domains quickly. Visual big picture. Easy to see flow, dependencies, and potential bounded contexts. Inherent event focus. Naturally leads to the discovery of meaningful events. Event storming is not just about events. It's a holistic domain modeling technique that directly informs the design of your event source system. 2. Example mapping. Example mapping is a collaborative technique, often with specification by example or behavior-driven development, that helps clarify business rules and edge cases. While not directly designed for event discovery, it helps identify the different outcomes or facts that can occur from a specific action, which can then be modeled as events. How it works. Inputs, a user story or a feature. Process, for a given rule, identify concrete examples, happy path, sad path, edge cases. Rules, blue card, define the business rule. Examples, green card, provide concrete scenarios that illustrate the rule. Each example implicitly defines a specific outcome. Questions, red card, any uncertainties or ambiguities that arise during the discussion. Event relation, the outcome of an example often directly translates into an event. Rule, users cannot order items that are out of stock. Example, if user tries to order 3 widget X, but only 2 are in stock, then order is rejected. Implied event, order rejected with a reason, insufficient stock. Benefits, helps uncover the precise circumstances under which different events might occur, ensuring rich and accurate event data. What makes a good event? Granularity, intent, immutability. Once you've discovered potential events, it's crucial to refine them. A well-designed event possesses several key characteristics. Granularity, just right, not too fine, not too coarse. Too coarse, an event like order updated or customer changed is too generic. It doesn't convey what specific business fact occurred. Consumers of such events would have to guess or query state to understand the change, undermining the event's purpose. Too fine. Breaking down a single business fact into multiple events can lead to an explosion of events that are hard to coordinate. Example, customer first name changed, customer last name changed, customer address line 1 changed instead of customer shipping address changed, or a more general customer details updated, if the business always updates these together. Just right, an event should represent a single, cohesive business fact that is meaningful to the domain. Shipping address changed, item added to cart, order canceled, these are specific, clear, and business relevant. Intent revealing name. The name should clearly state what happened, using the ubiquitous language in the past tense. Avoid technical jargon unless it's also part of the domain's language, e.g., checksum might be, database ID probably isn't. Example, payment received clearly states intent. Transaction completed is less specific. Immutability and factuality. An event is a record of something that already happened. It's a statement of fact. It cannot be changed or undone. If a correction is needed, a new event representing the correction, e.g., payment refunded, order correction applied, is created. Self-contained and complete. An event should contain all the necessary data to describe the reported occurrence at the time it happened. Consumers of the event should ideally not need to query another system or the aggregate root to understand the event's context or meaning. Example, a product price changed event should contain the producted, the old price, the new price, and the timestamp. It shouldn't just contain the new price and expect consumers to look up the old one. Capturing necessary data within events. When designing the payload, the data content of an event, aim for completeness, relevance, and semantic richness. Identify core attributes. What are the absolute minimum data points needed to describe this particular business fact? For order placed, ordered, customered, line items, each with producted, quantity, unit price, total amount, order date. For shipping address changed, ordered, old address, new address. Include contextual data. Sometimes, data that isn't directly part of the change is important for consumers. Userid or actorid. Who initiated this action? Crucial for auditing. Timestamp. When did this event occur? Essential for ordering and temporal queries. Correlationid or causationid. If this event was caused by another message or process, include an ID to link them. Useful for tracing distributed transactions. Use value objects. Instead of simple data types, use rich DDD value objects where appropriate. Instead of string street, string city, string zip code, use an address value object. Instead of decimal amount, use a money value object. This provides type safety, encapsulates validation, and aligns with your domain model. Avoid redundancy within the event. While events should be self-contained, avoid including data that is clearly derivable from other data within the same event or state that is not directly affected by the event's occurrence. An order-placed event doesn't need to contain the customer's full address if that address is stored on the customer aggregate and merely referenced by customer id. Dealing with transient states and commands versus events. A common confusion when modeling events is distinguishing between commands, transient states, and the final event. Commands, e.g., place order, change shipping address, are intentions or requests. They are imperative. They represent what you want to happen. They are typically handled by an aggregate. Events, e.g., order placed, shipping address changed, are facts. They are declarative. They represent what has already happened. They are produced by an aggregate and stored. A system might internally go through transient states, e.g., payment initiated, payment processing, before a final, meaningful event, payment received or payment failed, is emitted. It's usually best to only emit events for the significant outcomes that the business cares about, not every single internal step of a process. If a transient state is meaningful to the business and needs to be observable or auditable, then it should be an event. If it's purely an internal technical detail, it might not warrant its own domain event. By carefully applying these principles and techniques, you can craft a set of events that not only provide a robust foundation for your event source system, but also serve as a clear, precise, and auditable narrative of your business domain. This meticulous event modeling is where the magic of event sourcing truly begins to transform your software. Next, we will explore the core design patterns that underpin the implementation of event sourcing, from the aggregate pattern to the event store. 6. Core design patterns in event sourcing. With a solid understanding of fundamental event sourcing concepts and the critical role of domain-driven design and event modeling, we can now turn our attention to the concrete architectural patterns that enable us to build event-sourced systems. These patterns dictate how we manage state, persist events, and retrieve them to reconstruct an entity's history. The aggregate pattern revisited for event sourcing. We previously discussed the aggregate as a consistency boundary in DDD. In event sourcing, the aggregate is the most crucial design pattern for managing write operations and ensuring transactional integrity. How it works in event sourcing. Command reception. An aggregate receives a command, e.g., change customer address command. Load state. To process the command, the aggregate needs its current state. It reconstructs this state by loading its entire event stream from the event store and applying each event in chronological order to an initial, empty state. This process is often called rehydration. Decision and event generation. With its current state in memory, the aggregate performs the requested operation. It validates the command against its business rules and its current state. If valid, it produces one or more new domain events, e.g., customer address changed. These new events represent the changes the command intends to make. Apply events to self. Crucially, before persisting them, the aggregate applies these newly generated events to its own in-memory state. This ensures that the aggregate state is always consistent with the events it's about to persist. This step is identical to how it rehydrates its state from past events. Persist events. The newly generated events are then appended to the aggregate's specific event stream in the event store. This is the only way an aggregate state can change persistently. Concurrency control. The event store typically ensures that only one set of events can be appended to an aggregate stream at a given version. If two commands attempt to append events based on the same prior version, one will fail with a concurrency conflict. This optimistic concurrency control ensures consistency without complex locking mechanisms. Why this pattern is essential. Transactional consistency. All changes to an aggregate, and thus its internal invariants, are captured atomically within a single batch of events appended to its stream. Encapsulation. The aggregate hides its internal state and only exposes behavior through commands and emitted events. This enforces strict adherence to business rules. Scalability. Since aggregates operate largely independently, they can be processed concurrently, improving throughput. Challenges and considerations. Aggregate size. Large aggregates with very long event streams can lead to slow rehydration times. This is where a pattern like snapshotting, discussed later, comes in. Defining boundaries. Correctly identifying aggregate boundaries, order or order item as separate aggregates, is critical and often challenging, as discussed in the DDD chapter. Poorly defined boundaries can lead to performance issues or distributed transaction complexities. The event store pattern, implementation strategies. The event store is the heart of an event-sourced system, serving as the definitive ledger of all business facts. Its primary responsibility is to store event streams reliably and provide mechanisms to retrieve them. Key characteristics and implementation considerations. Append-only log. Events are always appended. This simplifies the underlying data structure and leverages the performance of sequential writes. It also makes auditing straightforward. Stream per aggregate. Events are organized into logical streams, almost always one stream per aggregate instance. This allows for efficient retrieval of an aggregate's history. Optimistic concurrency. When appending events, the event store usually checks the expected version of the stream. If the actual current version doesn't match the expected version, it signals a concurrency conflict. This prevents data loss from simultaneous updates. Idempotence. While the event store itself is append-only, the clients interacting with it, e.g., event producers, event consumers, may need to handle idempotent operations. The event store can help by, for example, rejecting events with duplicate IDs. Global event stream. In addition to per aggregate streams, many event stores also provide a global, ordered stream of all events across the entire system. This all stream is vital for building projections and coordinating across different bounded contexts. Typical implementation strategies. Dedicated event store products. Solutions like EventStoreDB are designed specifically for event sourcing. They offer robust features like efficient append-only storage, stream versioning, subscriptions, and projections. Relational databases. While not purpose-built, relational databases can be used. You would typically create a table like events with columns such as evented, streamed, aggregate ID, stream version, event type, payload, JSON, XML blob, timestamp. Ensuring efficient appending and optimistic concurrency requires careful indexing and transactional guarantees. NoSQL databases. Document databases, like MongoDB, Couchbase, or column family databases, like Cassandra, can also be used. They might offer flexible schema for event payloads. The challenge is typically managing efficient stream ordering and strong consistency for optimistic concurrency. Message brokers as event logs with careful engineering. Tools like Apache Kafka are often used as event log systems. They naturally support append-only, ordered streams, topics, partitions, and provide robust subscription models. However, Kafka itself is not a transactional data store in the way EventStoreDB or a relational database is designed for ACID guarantees per aggregate. You'd need to layer transactional mechanics, e.g., outbox pattern on top. The choice of event store implementation can significantly impact system performance, operational complexity, and feature availability. The event stream pattern. Reading, appending, and subscribing. Building on the event store, the event stream pattern defines the core operations for interacting with your event data. Appending events. This is the most crucial write operation. A new batch of events is atomically added to the end of a specific aggregate stream. This operation includes optimistic concurrency checks, e.g., append these n events to stream XYZ only if its current version is V. Reading a stream rehydration. To reconstruct an aggregate state, you read all events from a specific stream from its beginning up to its current version. Get events, stream ID from version to version. Reading all streams, global stream. To build projections or feed other bounded contexts, you read all events from the global event stream, ordered chronologically. This is often done by subscribing to new events. Read all events from global position. Subscriptions. This mechanism allows other components, e.g., projection builders, process managers, other microservices, to react to newly appended events in real time or near real time. Subscriptions can be persistent, maintain their position in the event stream, allowing them to resume processing from where they left off after a crash or restart. Volatile. Process events as they arrive, but don't track position, less common for critical projections. Grouped competing consumers. allow multiple instances of a consumer to process events from a single logical subscription, ensuring each event is processed only once by the group. Efficient implementation of these reading and appending operations is key to the performance of your event source system. Snapshotting, optimizing aggregate hydration. As an aggregates event stream grows, rehydrating its state by replaying hundreds or thousands of events can become a performance bottleneck. Snapshotting is a pattern designed to mitigate this. How it works: periodic state capture. Instead of replaying all events from the beginning of time, the aggregate state is periodically serialized and saved as a snapshot to the event store or a separate snapshot store. A snapshot represents the aggregate state after all events up to a certain version have been applied. Rehydration optimization. When an aggregate needs to be rehydrated, the system first attempts to load the latest snapshot. If a snapshot exists, the aggregate is loaded from that snapshot, and then only the events that occurred after that snapshot's version are replayed. Idempotent snapshots. Snapshots should be a derivable representation of state, not a source of truth. If a snapshot is corrupted or becomes outdated, it can be deleted and recreated by replaying all historical events from the event store. Example: an order aggregate has 500 events. Without snapshots, every time you want to modify that order, you replay all 500 events. With snapshots, perhaps after every 100 events, a snapshot is saved. If the latest snapshot is at version 400, then to rehydrate, you load the snapshot and only replay events 401 to 500. This significantly reduces rehydration time. Considerations for snapshotting. Frequency: too frequent and you spend too much time creating snapshots. Too infrequent and you miss out on performance gains. The optimal frequency depends on the aggregate's event rate and size. What to snapshot? Typically, the full aggregate state. Storage. Snapshots can be stored alongside events in the event store, e.g., as special events in the stream or in a dedicated snapshot store. Versioning. Snapshots must be tied to a specific event stream version to ensure correct replay of subsequent events. These core patterns form the backbone of any event source system. Mastering them is essential for building robust, performant, and scalable applications. In the next chapter, we will expand on these fundamentals by exploring more advanced patterns, particularly those related to orchestration and querying, like Sagas and CQRS. 7. Advanced design patterns, orchestration and querying. Once you have a firm grasp of the core event sourcing patterns, events, aggregates, event streams, and event stores, you'll quickly discover that real-world business processes often span multiple aggregates or even multiple bounded contexts. Furthermore, while the event store excels at preserving history, it's not optimized for answering complex queries about the current state of your system. This chapter delves into advanced patterns that address these challenges. Sagas, or process managers, for orchestrating long-running business processes and Command-Query Responsibility Segregation. CQRS, for efficient querying. Sagas and process managers, orchestrating long-running business processes across aggregates contexts. Many business operations are not simple, single transaction changes to one aggregate. Consider placing an e-commerce order. Customer places the order aggregate. Inventory needs to be updated, inventory aggregate context. Payment needs to be processed, payment aggregate context. Shipping needs to be arranged, shipping aggregate context. A notification needs to be sent, notification context. Each of these steps might involve different aggregates, potentially residing in different microservices or bounded contexts. How do you coordinate them, especially when failures can occur at any step? This is the problem that Sagas, often implemented as process managers, solve. A Saga, or process manager, is a long-running transaction that is orchestrated using events. It doesn't use traditional distributed transactions, which are rigid and prone to issues in distributed systems. Instead, a Saga coordinates a sequence of local transactions, each typically in operation on a single aggregate, using compensation logic. If a step in the Saga fails, compensatory actions are triggered for the previously completed steps to undo their effects, bringing the system back to a consistent state. How a Saga process manager works: triggers. A saga is usually initiated by a specific domain event, e.g., order placed. State management. The saga itself maintains a small, internal state tracking where it is in the overall process. This state is updated as it processes events and emits commands. In an event source system, the saga's state can also be event-sourced, meaning its process manager has its own stream of process started, step completed, step failed events. Command emission. Based on its current state and the received event, the saga decides what the next command in the sequence should be. It dispatches this command to the appropriate aggregate or service. Reaction to events. The saga then waits for events that indicate the outcome of the dispatched command, e.g., payment received, payment failed. Completion or compensation. If all steps complete successfully, the saga marks itself as finished. If a step fails, e.g., payment failed, the saga receives a compensating event and initiates commands to roll back previous successful steps, e.g., release inventory command. Example: order fulfillment saga. Trigger: order placed event. Saga action: send process payment command to payment service. Payment service emits payment received or payment failed. Saga receives payment received. Send reserve items command to inventory. Inventory service emits items reserved or insufficient stock. Saga receives insufficient stock. Send cancel order command to ordering and refund payment command to payment. Saga receives items reserved. Send arrange shipping command to shipping, and so on until the order shipped event marks saga completion. Benefits: loose coupling. Aggregates remain independent. The saga orchestrates without creating tight dependencies. Resilience. Designed to handle failures at any step gracefully through compensation. Transparency. The saga's state tracks the progress of complex processes, making it easier to monitor and audit. Considerations: complexity. Sagas add a layer of complexity. They are best used only when necessary for truly long-running, multi-aggregate processes. Eventual consistency. Sagas operate on the principle of eventual consistency. The overall process might take time to converge, and intermediate states might be inconsistent globally. CQRS, Command-Query Responsibility Segregation. The natural partner to event sourcing. As discussed in Chapter 2, event sourcing fundamentally separates the way you write data, appending events, from how you read data, reconstructing state from events. This separation is precisely what Command-Query Responsibility Segregation, CQRS, formalizes. CQRS proposes that you segregate the responsibility of handling commands, modifying state, from handling queries, retrieving state. This means having distinct models and potentially distinct data stores for writes and reads. The CQRS model, command-side write model, receives commands, e.g., place order command, loads and processes aggregates by replaying their event streams from the event store, emits new events which are appended to the event store, optimized for consistency and writes. Query-side read model/projection, receives queries, e.g., getOrderDetails query, queries highly optimized projections or materialized views. These projections are built asynchronously by consuming events from the event store, optimized for reads, performance, and flexibility. The synergy with event sourcing enables CQRS naturally. The event store acts as the central, immutable source of truth that feeds both sides. Write model, the aggregate logic operating on the event store, is your write model. Any write operation must go through the aggregate, which then emits events. Read model, your projections are your read models. They are built solely by reacting to events, forming specialized, denormalized views that are perfectly tailored to specific UI queries, e.g., a dashboard projection, a search results projection. Benefits of CQRS with event sourcing. Independent scaling. You can scale your write model, event store, and aggregate instances independently from your read models. If you have many reads but fewer writes, you can optimize your read infrastructure. Optimized data models for reads. Read models can be radically different from the write model. You can use different database technologies, e.g., relational for structured lists, NoSQL for schemaless documents, search engines for full-text search for different projections, each chosen for its query performance. Flexibility and evolvability. When business requirements change, you don't need to migrate all data to a new schema. You can simply create a new projection or modify an existing one and rebuild it from the entire historical event stream. This drastically reduces the pain of schema changes. Separation of concerns. Clear separation between commands and queries leads to cleaner, more maintainable codebases. Considerations. Eventual consistency. The most common challenge is managing eventual consistency. Users might perform an action, command, and then immediately query for the result, only to find the read model has not yet updated. Strategies like using correlation IDs, showing pending states in the UI, or polling can mitigate this. Increased complexity. CQRS adds more moving parts, event handlers, projection builders, potentially multiple read databases. It's not suitable for every application. Read models and projections, building efficient queryable views. As a follow-up to CQRS, let's elaborate on how projections are constructed. The process. A dedicated projection builder, or event handler, consumes events from the global event stream in chronological order. For each event it's interested in, it updates one or more read models. Database choice. The choice of database for a projection is entirely driven by query needs. Relational databases. Excellent for structured lists, aggregations, and complex joins, e.g. SQL Server, PostgreSQL. Document databases. Good for nested data, flexible schema, and quick reads by ID, e.g. MongoDB Couchbase. Search engines. Ideal for full-text search and faceted navigation, e.g. Elasticsearch, Apache Solr. Key value stores. For simple lookups, e.g. Redis DynamoDB. Rebuilding. As mentioned, a key advantage. If a projection becomes corrupted or its schema needs to change, it can be deleted and entirely rebuilt by replaying the entire event stream. This provides immense flexibility. Event handlers, reacting to events for side effects or state updates. Finally, event handlers are the active components that listen for and react to published events. They are the workhorses that update projections, trigger sagas, or initiate side effects, e.g., sending emails, integrating with external systems. Purpose: update read models projections, initiate sagas process managers, trigger external integrations, propagate events across bounded contexts if they cross boundaries. Loose coupling: event handlers typically run asynchronously, consuming events from a message queue or directly from the event store's subscription mechanism. This decouples the event producers from the event consumers. Idempotency: event handlers must be idempotent. This means processing the same event multiple times should produce the same result or no harmful side effects. This is crucial because message delivery systems can sometimes deliver events more than once. These advanced patterns, sagas and CQRS, are often seen as the hallmarks of sophisticated event-driven architectures. While they introduce complexity, they are indispensable tools for building scalable, resilient, and highly adaptable systems that truly harness the power of event sourcing, especially when dealing with distributed contexts and diverse querying needs. We'll delve into the practicalities of building read models in more detail in a later chapter. However, before that, we need to address a critical challenge. How do events, immutable historical facts, evolve as your business changes? This leads us to the topic of event evolution and versioning. 8. Event evolution and versioning, adapting to change. One of the most challenging aspects of building long-lived, event source systems is managing change, specifically the evolution of your events. The core principle of event sourcing is that events are immutable facts, stored forever. But what happens when your business requirements change and the structure or meaning of an event needs to evolve? This is where event versioning becomes crucial. Why events change over time? Events represent business facts. As businesses evolve, their understanding of these facts or the details associated with them can change. Consider an order-placed event. Initial version V1 might simply contain customer ID, order items, list of product ID, quantity, and total amount. Business change: the business introduces discount codes. Now, an order-placed event needs to track discount code and discount amount. This creates a need for order-placed V2. Further business change: the business starts offering personalized recommendations at the time of order. The order-placed event now needs to include recommended product IDs. This leads to order-placed v3. Or perhaps an attribute that was once optional becomes mandatory, or a string needs to become an enum, or a single field needs to be split into multiple fields. Each of these changes necessitates a strategy for handling existing, older versions of the event data without modifying them. Strategies for event versioning. Since you cannot change historical events, they are immutable facts, you need a strategy to enable new components of your system to understand and process old and new event versions, and for old components to gracefully handle new events. One tolerant reader/defensive programming. This is arguably the simplest and most robust strategy, and it applies primarily to backward compatibility. New consumers can read old events. It posits that consumers of events should be resilient to changes they don't expect. How it works: adding fields. New fields can be added to an event's payload. Older consumers simply ignore the new fields as they don't know about them. Newer consumers can read them. Removing fields carefully. Removing fields is trickier as it breaks older consumers needing those fields. If a field truly becomes obsolete and no older consumer needs it, it can be removed. A safer approach is to deprecate it and ensure no new producers create it, then remove it only once all consumers no longer depend on it. Renaming fields. This breaks both old and new consumers unless handled with aliases or explicitly mapped. Avoid renaming if possible. Type changes carefully. Changing a field's type, e.g., string to int, can break consumers. If necessary, consider adding a new field with the new type and deprecating the old one, or use a upcaster. See below. Implementation. Use JSON or similar flexible schema formats for event payloads. Implement robust parsing logic that can handle missing fields, e.g., provide default values. Avoid strict schema validation for incoming events on the consumer side. Use nullable types or optional constructs in your programming language. Pros: simplest to implement, allows for easy evolution within limits. Cons: not suitable for breaking changes, renaming, removing fundamental type changes. Can lead to complex, conditional logic in consumers if changes are frequent. 2 upcasters, event transformation. When a breaking change occurs, or when you explicitly want new versions of your domain objects to always receive the latest event structure. Upcasters, also known as event migrators or transformers, come into play. How it works: an upcaster is a piece of code that transforms an older version of an event into a newer version as it is being read from the event store. The original event in the event store remains untouched. Scenario: order-placed v1 needs to be transformed into order-placed v2, which adds discount amount. Upcaster logic. When a system reads order-placed v, the upcaster intercepts it, creates a new order-placed v2 instance, populates its fields from v1, and then adds a default or derived value for discount amount. The rest of the application then only sees order-placed v2. Chaining. Upcasters can be chained. v1, v2, v3. Each upcaster knows how to transform an event from n to n+1, where upcasters live. On read from event store, the most common approach. The event store itself, if it supports it, or the application layer reading from it applies upcasting. During replay, projection, rebuild. Used when rebuilding projections to ensure they always process the latest event structure. On aggregate rehydration. When an aggregate is rehydrated, its event stream might contain older versions that need to be upcasted before they are applied to the aggregate state. Pros: handles breaking changes gracefully without modifying historical data. Enables single, consistent view of event structure for the latest code. Cons: adds complexity to the read path. Upcasters need to be maintained for every version change. Over time, a long chain of upcasters can impact performance, though typically negligibly. 3 parallel streams/name versioning. This is often used in conjunction with tolerant reader and upcasters, rather than as a replacement. This strategy involves explicitly naming events with a version suffix, e.g., order-placed v1, order-placed v2. When a breaking change occurs, you simply start producing a new version of the event while keeping the old one in place. How it works. New event type. When order-placed needs a breaking change, you define a new event order-placed v and start producing it. Consumers handle both. Consumers must be updated to explicitly handle both order-placed V and order-placed V2. Aggregate decision. The aggregate logic might decide which event to produce based on its version. Less common, usually new code just produces the latest version. Pros, explicit about versions, simpler to reason about which code handles which event. Cons, requires consumers and producers to explicitly understand and manage multiple message types. Can lead to an explosion of event types if changes are frequent. Upcasting becomes more complex, as you might need to upcast V1 to V2 before processing, and so on. Backward and forward compatibility. When designing event versioning strategies, it's important to differentiate between backward compatibility, new consumers, old events. Can a newer version of your code read and understand older versions of your events? This is typically the more critical concern and is largely addressed by the tolerant reader pattern and upcasters. If you rebuild a projection, it must be able to process all past events, regardless of their version. Forward compatibility, old consumers, new events. Can an older version of your code gracefully handle a newer version of an event it doesn't recognize or understand? This is much harder to achieve for breaking changes, and often implies that you cannot push a new event producer without also updating all its consumers that need to understand that new event. For non-breaking changes, tolerant reader helps here. Older consumer ignores new fields. The general recommendation for achieving both is always use a tolerant reader approach for minor, non-breaking schema changes, adding new fields. Use upcasters for breaking changes, allowing new code to operate on a consistent, latest version of events while maintaining the immutability of stored facts. Avoid backward incompatible changes if possible. If you must do a renaming or restructure, use an upcaster. Schema evolution versus event content evolution. It's also important to distinguish between schema evolution, changes to the structure of an event, adding removing fields, changing types. This is what the versioning strategies above address. Event content evolution, changes to the meaning or semantics of an event. For example, product purchased might imply one thing, but later product sold might have a slightly different business meaning, even if its data structure is similar. This is more about domain modeling purity and is typically handled by introducing new event types if the business fact fundamentally changes, rather than trying to version the same event type. Managing event evolution is a continuous process that requires discipline and careful planning. It underscores the long-term commitment that event sourcing implies. It's a trade-off. The power of immutable history comes with the responsibility of meticulously managing event schema changes over time. By combining tolerant reading with a thoughtful approach to upcasting, you can ensure your event source system remains adaptable and maintainable for years to come. With a robust event model and versioning strategy in place, we can now discuss how to gain confidence in our system through effective testing. 9. Testing event source systems. Confidence in immutability. Testing is a critical component of any software development lifecycle, and event source systems are no exception. In fact, due to their unique properties, immutability of events, separation of read and write models, and temporal nature event, sourced applications lend themselves very well to certain testing methodologies, offering opportunities for exceptionally robust and clear test suites. However, they also introduce new considerations. The primary goal of testing in event sourcing is to ensure that aggregates behave correctly. They process commands, apply rules, and emit the right events. Projections correctly transform events into queryable read models. Process managers, Sagas, correctly orchestrate long-running processes by reacting to events and emitting commands. The entire system reliably stores, retrieves, and processes events. Testing aggregates, command-driven, event-observable. Testing aggregates in event sourcing is a highly effective and satisfying form of unit or integration testing. Since an aggregate state is entirely determined by its event stream, and its behavior is to process commands and emit new events, this forms a clear arrange-act-assert (AAA) structure. The test structure, arrange given. You start with a blank slate and then apply a sequence of past events to the aggregate to bring it to a specific state. This is exactly how the aggregate rehydrates itself in production. Act when you send a specific command to the aggregate, which is in the state you arranged. Assert, then, you verify two things. The aggregate emitted the expected sequence of new events. Optionally, the aggregate's internal state after applying those new events is as expected, though asserting on emitted events often suffices, as the internal state is a direct consequence of the events. No unexpected exceptions were thrown for valid commands, or the correct exception was thrown for invalid commands. Example test scenario for an order aggregate. Concept in actual code, this would be within a test framework. Given an order that has been placed and had items added. var order equals new order. Start with empty state. Order reply new order placed event order ID customer id. Order reply new order item added event order ID product today quantity A price A. Order reply new order item added event order ID product B quantity B price B. When we try to cancel an item, var command equals new cancel order item command order ID product today quantity A. Order handle command. Then an order item canceled event should be emitted. Var expected events new list domain event new order item canceled event order ID product today quantity A. To assert equal expected events order get uncommitted events. And the order's internal state should reflect the cancellation, e.g., total price reduced. Assert equal expected new total price order current total price. Benefits deterministic. Tests are highly deterministic because the aggregate state is precisely controlled by the events you apply. Clear state transitions. It clearly shows how the aggregate transitions from one state to another based on commands and events. Encourages pure functions. The apply method on events is typically a pure function, making it easy to test in isolation. Business-centric. The test expresses behavior in terms of business events and commands, aligning with the ubiquitous language. Considerations. Mocking the event store is usually unnecessary. For aggregate tests, you simulate the event store by simply providing the apply mechanism. These tests are typically fast as they run in memory. Testing projections read models. Event replay, state verification. Projections are built by consuming events. Testing them involves verifying that given a sequence of events, the read model ends up in the expected state. The test structure, arrange given, start with an empty read model database or an in-memory representation. Act when replay a specific sequence of events to the projections handler. This simulates the projection consuming events from the event store. Assert, then, query the read model and verify that the data matches the expected state. Example test scenario for a customer order list projection. Concept, given an empty customer order list read model. var projection equals new customer order list projection in memory database. When these events occur. Projection handle, new customer registered event, customer ID name. Projection handle, new order placed event, order ID 1, customer ID total 1. Projection handle, new order placed event, order ID 2, customer ID total 2. Projection handle, new order canceled event, order ID 1, 1 order canceled. Then the customer order list should contain the correct data. var customer orders equals in memory database query. Select from customer orders where customer ID equals at customer ID, customer ID. Assert single customer orders .count, only one active order. Assert equal order ID 2 customer orders first, order ID. Assert equal total 2 customer orders first, estimated total price. Assuming cancellation affects estimated price, or a different total will exist. Benefits, disposable read models. As read models are disposable in production, they are equally disposable in tests, making setup and teardown simple. Regression friendly. Replaying event streams makes it easy to test for regressions if projection logic changes. Database agnostic, initially. You can often use an in-memory representation of your red model for faster tests, only using real database integrations for higher-level integration tests. Considerations. Ensuring idempotency for event handlers is crucial, and these tests can help verify it implicitly. Testing eventual consistency directly is harder here. This focuses on the projection logic itself. Testing process manager Sagas. simulating event flows. Testing sagas can be more complex due to their asynchronous, long-running nature and their interaction with multiple aggregate services. The goal is to ensure the saga correctly orchestrates by emitting the right commands in response to specific events, and that it maintains its state correctly. The test structure, simulated environment, arrange, given. Initialize the saga process manager. It may have an initial state or be empty. Act when, inject a sequence of incoming events that the saga consumes. Assert then. Verify the commands that the saga emits in response, and optionally, verify the saga's internal state transitions. Example test scenario for an order fulfillment saga. Concept: given a new order fulfillment saga, var saga equals new order fulfillment saga when an order placed event occurs. Saga handle, new order placed event, order ID. Then the saga should emit a process payment command. Assert single, saga get outgoing commands. Assert is type process payment command, saga get outgoing commands. First, when a payment failed event occurs for that order. After the first command has been processed externally and failed. Saga handle, new payment failed event, order ID. Then the saga should emit a request customer confirmation of cancellation command. Assert single, saga get outgoing commands. Assert is type request customer confirmation of cancellation command, saga get outgoing commands. First, benefits, logical flow validation, explicitly validates the complex, multi-step orchestration logic. Separation of concerns, tests the saga's logic in isolation from the actual services it interacts with. Considerations, real-world sagas can be complex. Tests should focus on clear scenarios, happy path, specific failure modes. Mocking external systems, or even other aggregates, might be necessary to control outcomes and keep tests performant. Integration, testing the event store and subscribers. While the above tests focus on the business logic, you also need to ensure that the actual event store and your event subscription mechanisms work as expected in your deployment environment. Event storage and retrieval. Test that events genuinely persist to your chosen event store and that you can reread them correctly. This might involve setting up a test database instance and performing simple write-read operations. Concurrency handling. Verify that your event store setup correctly handles optimistic concurrency conflicts and that your application logic responds appropriately, e.g., retrying commands. Subscription reliability. Test that subscribers reliably receive events, even under load or transient network issues. This includes testing persistent subscriptions, ensuring they pick up from the last processed event after a restart. Projection rebuilds. A critical integration test involves simulating a full projection rebuild. This is often an expensive test, but it verifies the entire chain from history replay to read model state. Automated testing and test data. Harnessing the power of event sourcing, you can create test data by simply writing a sequence of events to the event store. This data is perfectly reconstructible and auditable. For complex scenarios, instead of manually setting up database states, you can build them by scripting event streams, which is highly repeatable and transparent. In summary, event sourcing fundamentally changes how you think about testing, largely for the better. The immutability of events and the clear separation of concerns, commands, events, projections, leads to tests that are more deterministic, more expressive of business intent, and often faster than traditional transactional tests. By applying these strategies, you can build high confidence in the correctness and reliability of your event source systems. 10. Building read models and querying event data in practice. As we've explored, event sourcing fundamentally separates data persistence from data querying. While the event store serves as the definitive source of truth for all changes, it is ill-suited for direct queries that demand immediate, aggregated views of the current state. This is where read models, also known as projections, become indispensable. This chapter dives into the practicalities of building and managing these query-optimized views from your stream of events. The role of read models in CQRS. Recall that CQRS stands for Command-Query Responsibility Segregation. In an event-sourced system, the right side, where commands are processed and events are appended to the event store, is inherently different from the read side. Read models are the actual materialized data structures that serve the query side. A single set of events can feed multiple, diverse read models, each tailored for a specific query or user interface. For example, a current order status read model for a detailed view of a single order, and customer order history read model for listing all orders of a customer. A sales dashboard read model for aggregated sales statistics. A shippable orders read model containing only orders ready for shipment. Each of these would be constructed by processing the same stream of order placed, item added, payment received, order shipped events, but filtering and aggregating them differently to serve their unique query needs. Choosing the right database for read models. One of the significant advantages of CQRS and read models is the freedom to choose the most appropriate database technology, or even flat files, for each specific query need, rather than forcing all data into a single, potentially ill-fitting database. Common choices include relational databases, e.g., PostgreSQL, MySQL, SQL Server. When to use. Excellent for highly structured data, complex joins, strong consistency requirements for the read model itself, and when you need to run analytical SQL queries. Good for lists, dashboards, and detailed entity views. Pros: mature, well-understood, powerful querying capabilities, SQL, transactional within the read model, good for reporting. Cons: can be less flexible for rapidly changing schemas, may struggle with very high write-read throughput compared to NoSQL for specific patterns. Document databases, e.g., MongoDB, Couchbase, when to use. Ideal for denormalized, flexible data structures where a single query often fetches a large, self-contained document, e.g., full order details, user profiles. Great for UI-centric views that map directly to screen layouts. Pros: flexible schema, schemaless, easy to store complex nested objects, scales horizontally well, high read and write throughput for document-centric access. Cons: less suitable for complex joins or strong aggregation across many documents and less pre-aggregated. Transactions across multiple documents are harder. Search engines, e.g., Elasticsearch, Apache Solr. When to use: paramount for full-text search, faceted search, and complex filtering. Can also be used for analytical dashboards. Pros: highly optimized for text-based queries, powerful indexing, real-time search capabilities. Cons: data typically needs to be pushed here from a primary source, not generally used as a primary data store. Eventual consistency can be higher latency. Key value stores, e.g., Redis, DynamoDB, Cassandra. When to use: for very simple, high-performance lookups by key or for caching results. Pros: extremely fast read-write, high scalability, simple API. Cons: limited querying capabilities. You usually need to know the exact key. Graph databases, e.g., Neo4j. When to use: when your data has complex relationships and you need to query connections, e.g., social networks, recommendation engines. Pros: optimized for traversing relationships, expressive query languages for graphs. Cons: niche use may require different skill sets. The choice is not exclusive. You can use multiple databases, each serving a different read model based on its strengths. Rebuilding projections from scratch. One of the most powerful features of event sourcing is the ability to rebuild a read model from scratch by replaying the entire history of events from the event store. When to rebuild: schema changes. When you change the structure of a read model, e.g., adding a new field, changing how data is aggregated. Instead of struggling with database migrations, you just drop the old table collection and rebuild. Bug fixes: if there's a bug in your projection logic that caused your read model to become corrupted, you fix the bug, drop the read model, and rebuild it. New read models. When you need a completely new view of your data for a new feature or report, you create a new projection handler and build the read model from scratch. Data consistency issues. In rare cases of data inconsistencies in the read model, a rebuild can restore sanity. The process: stop projection handler. Temporarily stop the process that's updating the specific read model. Drop/clear read model. Delete all data from the target read model database. Start replay from scratch. Start a dedicated process that reads all events from the event store's global stream, starting from the very first event, position 0. Process events. The rebuild process feeds these historical events in chronological order through the projection handler. Monitor progress. For large datasets, monitoring the progress of the rebuild is important. Switch over. Once the rebuild is complete and the read model is up to date, you can switch your application to use the newly rebuilt read model and restart the real-time projection handler. Optimizations for rebuilds. Parallel processing. For very large event streams, you can often parallelize the replay by segmenting the events or running multiple projection instances. Batching. Process events in batches rather than one by one to reduce database write overhead. Offline rebuilds. Perform the rebuild on a separate instance or infrastructure to minimize impact on production. Handling eventual consistency in UIs. Since read models are built asynchronously by processing events, they are eventually consistent. This means there's a small but perceptible lag between a command being successfully processed and events saved to the event store, and the read model reflecting that change. For many user-facing applications, this is the most common challenge in CQRS and event sourcing. Strategies to manage eventual consistency in UIs. Embrace it, acknowledge, and accept. For many scenarios, e.g., a sent mail folder where the email is displayed after it's sent, a few seconds of delay is perfectly acceptable. Communicate this to users if necessary. Optimistic UI updates. The UI can optimistically update the displayed state before the read model has caught up. When a user clicks Place Order, the UI immediately shows Order Placed or Order Processing, regardless of the read model. If the command fails, rare if aggregate validation is good, the UI can revert or show an error. This provides immediate feedback to the user, but introduces risk of showing incorrect data if the command ultimately fails or the projection lags significantly. Polling WebSockets. For critical updates, the UI can periodically poll the red model for the updated state, or use WebSockets server sent events to receive real-time updates as they appear in the read model. Correlation IDs. Pass a correlation ID from the command through to the events and into the read model. The UI can then wait for a red model update that carries that specific correlation ID. Command-sourced UI data. For certain specific, critical views, e.g., the shopping cart before checkout, the UI can bypass the read model and directly query a small, well-defined piece of the right model's state, e.g., retrieving the current cart state directly from the shopping cart aggregate if it doesn't involve complex queries. This usually implies doing a live rehydration of the aggregate. This should be an exception, not the rule, as it bypasses the primary purpose of read models. Eventual consistency indicators. Display a visual cue, e.g., processing, pending, until the read model has certainly caught up. The key is to understand the consistency requirements of each specific user interaction and apply an appropriate strategy. Not every query needs strong consistency. Real-time versus batch projections. Real-time projections. These are the most common. They consume events as they are appended to the event store, often via subscriptions, and update the red model almost immediately. This is suitable for most user-facing applications. Batch projections. Some read models, especially for analytics or reporting, don't need to be updated in real time. They can be built or updated periodically, e.g., nightly batch jobs, by processing events in chunks. This can be more efficient for very large datasets where aggregation is computationally intensive. Building red models is an iterative process. You start with fundamental views, then refine them based on performance observations and evolving query requirements. The flexibility of event sourcing, combined with the power of modern database technologies, empowers you to create highly performant and adaptable query experiences from your rich event data. With your system's data model defined and queryable, the next step is to prepare it for the real world. 11. Event sourcing in practice. Implementation considerations. Moving from theoretical understanding to practical implementation of event sourcing involves navigating a new landscape of technical considerations. While the core patterns are defined, their application in a live system requires careful thought about error handling, concurrency, idempotence, and sharing events across larger system boundaries. This chapter delves into these crucial implementation details that make or break a production-ready event-sourced application. Error handling and compensating transactions. In distributed systems, failures are inevitable. In an event-sourced system, especially with Sagas, the concept of compensating transactions becomes key, replacing traditional atomicity, consistency, isolation, durability, transactions across services with an eventually consistent model. Atomicity within the aggregate. Remember that the act of generating new events and writing them to the event store for a single aggregate is atomic. Either all new events are saved for that aggregate, or none are. This preserves internal consistency. Errors here typically mean the command fails and no events are written. Errors during command processing. If an aggregate receives a command it cannot process, e.g., due to invalid state, invalid input, it should reject the command and ideally return a meaningful error message to the caller. No events are produced. Handling event handler failures. Event handlers, the components building read models or triggering Sagas, operate asynchronously. If an event handler fails to process an event, retry mechanisms. The system must ensure dead letter queues or persistent retries for failed event processing. The event handler should use idempotent operations when updating read models to handle retries safely. See idempotence below. Monitoring and alerting. Alerts should be triggered for persistent failures in event handlers so operations teams can intervene. Compensating actions in Sagas. As discussed in Chapter 7, Sagas manage multi-step processes. If a step in a Saga fails after previous steps have completed, the Saga initiates compensating transactions. These are new commands sent to previously involved aggregates or services to undo or reverse the effects of the earlier successful steps. Example, payment processed successfully, but shipping failed. The Saga sends a refund payment command. This highlights the importance of designing reversible operations within your domain. Debugging event source systems. Debugging an event source system can feel different from debugging a traditional CRUD system. You cannot simply inspect a database table to see current state and understand its history. Event stream is your debugger. The primary debugging tool is the event stream itself. By inspecting an aggregate's event stream, you can see every action that led to its current state. Many event store implementations provide UIs or tools to browse event streams. Reproducing issues. If you have a bug, you can often replay the exact sequence of events that led to the problem in a test or development environment. This allows for highly precise reproduction and diagnosis. Logging. Events themselves are valuable logs. Supplement this with application logging of commands received, internal aggregate logic execution paths, and event handler processing. Ensure correlation IDS are carried through logs for distributed tracing. Read model inspection. While the event store is the source of truth, the read models are what your application queries. Inspecting the read model can tell you what the application sees. If the read model is incorrect, the next step is often to check the events that built it and the projection logic. Saga visualizers. For complex sagas, visual tools that show the state transitions and emitted commands can be invaluable. Dealing with idempotence and concurrency. Idempotence. An operation is idempotent if applying it multiple times produces the same result as applying it once. In distributed event-driven systems, guarantees are often at least once delivery, meaning events and commands might be delivered more than once due to network issues, retries, or consumer crashes. Therefore, all operations that modify state, commands, event handlers must be idempotent. Aggregate command handling. Commands should typically have a commanded, a unique GUID. The aggregate can store the commanded of the last command it processed. If it receives a command with an id that has already been processed, it can simply ignore it or return the result of the previous processing. Events also often have a unique evented. The event store itself typically handles idempotent appends, ensuring an event is only added once based on its ID and the stream version. Event handlers projections. When an event handler processes an event to update a read model, it should ensure that if it receives the same event again, it doesn't corrupt the data. Strategies: version-based updates. Update a record only if the event's version is newer than the last processed event version on that record. Conditional writes, upsert. Use database features like UPSERT with conflict detection. Idempotent operations. Design updates to be inherently idempotent, e.g., set quantity to X rather than add Y to quantity. Store the evented in the red model alongside the data and only process events whose evented hasn't been seen before. Concurrency. Event sourcing largely handles concurrency at the aggregate level using optimistic concurrency control. When an aggregate is loaded, its current version, expected version, is noted. When a command is processed, new events are proposed with this expected version. The event store only allows these new events to be appended if the stream's current version still matches the expected version. If another process has already appended events to that stream, incrementing its version, the append operation will fail. Concurrency conflict. Handling concurrency conflicts. The application code must be prepared to handle these conflicts. Typical strategies include retry. The simplest solution is to retry the entire command processing cycle, reload the aggregate, rerun the command against the new state, and attempt to save. This works well for transient conflicts. User notification. For non-transient, business logic-based conflicts, e.g., two users trying to cancel the last item in stock, the system might need to notify the user of the conflict and ask them to reevaluate their action. This requires careful UI/UX design. Sharing events across bounded contexts. Events are an excellent mechanism for communication between different bounded contexts, often implemented as microservices. Mechanism. Typically, a bounded context produces events into its own event store. These events are then published to a message broker, e.g., Kafka, RabbitMQ, Azure Service Bus, that acts as an event bus. Subscribing and consuming. Other bounded contexts that are interested in these events subscribe to the relevant topics queues on the message broker. They consume these published events and react to them, often by updating their own internal aggregates or read models. Translation. It's important to use the ubiquitous language of the publishing context for the events. If a consuming context needs to interpret or map these events to its own ubiquitous language, it should perform that translation internally. Context mapping patterns from DDD, like anti-corruption layers, might be needed, especially when integrating with legacy systems. Event schema and versioning. This becomes even more critical when sharing events across bounded contexts, as a change in one context's event schema can break others. Hence, the versioning strategies discussed in Chapter 8 are paramount. Semantic versioning of events, e.g., order v1 placed or order v2 placed, is good practice. Security considerations. Security needs to be woven into the fabric of your event source system. Authorization for commands. Just like any other system, commands hitting your aggregates must be authorized. Verify the user's permissions before allowing them to execute a command. This is typically done at the service entry point, e.g., API gateway, domain service layer. Authentication and identity. Ensure that the actor performing a command is properly authenticated. Include the actorid or userid as metadata in your events for a robust audit trail. Data and events. Be mindful of sensitive data in event payloads. Encryption. Encrypt sensitive fields within event payloads at rest in the event store. PII-Fi minimization. Only include necessary sensitive data. Consider tokenization or hashing for fields like credit card numbers or personally identifiable information. PII, if they don't need to be read in plain text historical events. If you need to forget data, e.g., GDPR right to be forgotten, this becomes a complex challenge for immutable events, often requiring re-encryption with new keys or special handling like marking events as erased and implementing filters on reads. Read model security. Read models, as denormalized views, are often queried by the presentation layer. Access to these models must also be secured, potentially filtering data based on the user's role or scope. Event handler permissions. Event handlers typically run with elevated permissions as they are internal system components. Ensure their access to databases and external services is appropriately scoped. Implementing event sourcing effectively requires addressing these practical concerns head-on. By designing for resilience, error handling, idempotence, manageability, debugging, auditability, and secure and interoperable communication, event sharing, concurrency, security, you can build robust and powerful applications that truly leverage the benefits of an event-driven architecture. Next, we will explore how to scale these systems to handle ever-increasing demands. 12. Scaling and performance with event sourcing. One of the significant advantages, often attributed to event sourcing, is its potential for high scalability and performance. By separating concerns, writes versus reads, aggregates versus projections, and embracing asynchronous processing, event source systems can be designed to handle substantial loads. However, achieving this performance requires careful design and optimization at various levels. Horizontal scaling of aggregates and read models. The nature of event sourcing inherently lends itself to horizontal scaling. Aggregates, right side. Since each aggregate largely operates independently and typically updates only its own event stream, event source systems can easily spread their write workload across multiple instances. The event store needs to efficiently handle concurrent appends to different event streams. Modern event stores, like EventStoreDB, or distributed logs, like Kafka, are designed for high-throughput, concurrent writes, often relying on partitioning strategies. The processing of commands by individual aggregate instances can be distributed across many application servers or containers. Read models, query side. Read models, being materialized views, are completely decoupled from the write operations. This allows them to be scaled independently based solely on query load. Need to scale reads? Add more replicas of your read model database. If using a NoSQL database, you can scale almost linearly by adding more nodes to the cluster. Different read models can scale differently. A highly accessed dashboard might run on a large cluster, while a less used historical report might run on a smaller, more cost-effective setup. Since read models can be rebuilt from events, introducing new read model instances, e.g., for data locality or higher availability regions, is straightforward. Simply deploy a new instance and let it replay all events. Event store performance and scalability. The event store is a critical component, as it's the bottleneck for all write operations. Its performance directly impacts the throughput of your system. Sequential writes. Event stores are optimized for sequential writes, appends, which are inherently faster than random writes common in traditional databases. This allows them to sustain very high write rates. Partitioning. For extreme scale, events are often partitioned by streamid aggregate ID. This means events for different aggregates can be written to different physical partitions, allowing for parallel writes and reducing contention. Replication clustering. High availability and read scalability of the event store itself are achieved through replication and clustering. Events are replicated across multiple nodes to ensure durability and availability in case of node failures. Latency, the most critical performance metric for the write side, often becomes the latency of appending events. Low latency is crucial for responsiveness to commands. Optimizing event stream reads. While appending events is fast, reading an aggregate's entire event stream for rehydration can become slow if the stream contains many events, often leading to a performance bottleneck. Snapshotting. As discussed in Chapter 6, snapshotting is the primary technique for optimizing rehydration. By taking snapshots periodically, the aggregate only needs to replay events from the last snapshot forward, significantly reducing the number of events to process. Caching. External caches, e.g., RIDIs. The hydrated state of an aggregate can be cached in an external key-value store after it has been processed. Subsequent commands can then load the state from the cache, reducing calls to the event store and event replay overhead. Invalidation upon new event writes, or relying on a time-to-live, is crucial. In-memory caching. For rapidly processing a series of commands for the same aggregate, an in-memory cache within the application instance can be used. Hot-cold data strategy. Not all aggregates are accessed with the same frequency. Long-lived aggregates that are rarely modified, cold data, might tolerate higher rehydration costs, while frequently modified ones, hot data, need aggressive snapshotting or caching. Aggregate size. Designing smaller, focused aggregates, using DDD principles and clear bounded contexts, naturally leads to shorter event streams, mitigating the rehydration problem. However, this must be balanced against ensuring consistency. Dealing with large aggregates and event streams. While smaller aggregates are generally preferred, some domains naturally lead to large aggregates or long event streams, especially those representing master data or single entities that accumulate many changes over time. Example, customer aggregate in an HR system. A single employee record might have thousands of events over many years: job changes, salary adjustments, address changes, performance reviews. Strategies. Snapshotting. Essential for large aggregates. Decomposition, where possible. Can the large aggregate be broken down into smaller, more focused aggregates without violating consistency boundaries? For example, instead of one customer aggregate holding all details, perhaps a customer profile aggregate and a separate customer payroll details aggregate. This is a DDD decision first and foremost. Archiving old events. For very old, rarely accessed events, some event store implementations allow for archiving to cheaper, slower storage. This might mean rehydration requires fetching from archived storage, but it could be acceptable for some scenarios. Contextual aggregates read only aggregates. Sometimes, a portion of a large aggregate can be treated as an immutable history for most purposes, with only specific aspects allowing changes, e.g., historical address records versus current address, distributed transactions, and coordination. One of the driving motivations for event sourcing and event-driven architectures is to avoid distributed transactions that span multiple services or databases. Traditional two-phase commit 2PC transactions are notoriously slow, prone to deadlocks, and difficult to scale in distributed environments. Eventual consistency as the norm. Event-sourced systems embrace eventual consistency. Changes across different aggregates or services are coordinated asynchronously through event publication and subscription. Sagas process managers. As detailed in Chapter 7, Sagas are the pattern for orchestrating workflows that logically span multiple services. They achieve consistency through a series of local transactions and compensating actions, rather than a single, global ACID transaction. This is a more scalable pattern for distributed systems. Outbox pattern. When an aggregate saves events to its event store, it often needs to publish these events to a message broker for other services to consume. To ensure atomicity between saving events and publishing them, i.e., you don't save events without publishing or publish without saving, the outbox pattern is commonly used. How it works. Instead of directly publishing events after saving to the event store, the events are also saved into an outbox table within the same transaction as the events are saved to the event store. If using a relational database-based event store, a separate, dedicated process then pulls this outbox table, publishes the events to the message broker, and marks them as sent. This guarantees that events are only published if they are successfully saved. If using a purpose-built event store, this is often handled internally. API Gateways BFFS backend for frontend. For coordinating multiple calls to different microservices from a client application, an API gateway or a backend for frontend BFF pattern can be used. The gateway aggregates results from multiple services or orchestrates initial commands, abstracting the underlying distributed nature from the client. Scaling event source systems is about leveraging their inherent properties of decoupling and asynchronous communication. By judiciously applying patterns like snapshotting, choosing appropriate event store solutions, and embracing eventual consistency patterns like Sagas and the Outbox, you can build applications that are not only robust and auditable, but also capable of handling significant operational demands. The performance gains often come from the freedom to optimize each component, write model, various read models, independently using the best fit technology. 13. Going live. Deployment, operations, and monitoring. Bringing an event-sourced system into production requires careful planning and robust operational practices. While the development benefits of event sourcing are compelling, the operational landscape presents unique challenges and opportunities. This chapter focuses on the practical aspects of deploying, running, and maintaining your event-sourced architecture in the real world. Deployment strategies for event-sourced applications. Deploying event-sourced applications often involves deploying multiple, distinct services that communicate asynchronously via events. Microservices mindset. Event sourcing naturally aligns with a microservices architecture. Each bounded context or a group of related aggregates can be deployed as independent services. This allows for independent deployment of components. Decoupled components. Deploy your event store or its underlying database, your aggregate handling services, write model, and your various projection read model services independently. This allows you to update one without affecting others, as long as event contracts are honored. Rolling updates. When deploying new versions of your services, e.g., a new version of an aggregate service, use rolling updates. Ensure backward compatibility of your event contracts so that older versions of event consumers, projections, Sagas, can still process events from newer producers during the transition. Blue, green, or canary deployments. For more critical components, especially event store or core aggregate services, consider blue, green, or canary deployment strategies to minimize downtime and risk during updates. With immutable events, if a blue-green deployment strategy causes an issue, you can safely roll back and nothing has been overwritten. Event store deployment. Your event store is a critical piece of infrastructure, deserving a robust deployment strategy. This typically involves clustered deployments for high availability and fault tolerance, often across multiple availability zones. Operational best practices: backup, recovery, replay. The event store is your primary source of truth. Its operational integrity is paramount. Backup and restore. Full event store backup. Regularly backup your entire event store. Since it's an append-only log, backups are typically easier than traditional relational databases. You can often simply copy the underlying data files. Point-in-time recovery. Implement a strategy for point-in-time recovery. This might involve continuous archiving of events, e.g., to cold storage like S3, combined with periodic full backups. Your RTO, recovery time objective, and RPO, recovery point objective, drive this decision. Projections as disposable. Remember that your read models are largely disposable. If there's an issue with a read model, the primary recovery strategy is usually to delete it and rebuild it by replaying events from the event store. Backup of read models is often secondary to the event store backup. Data integrity checks. Regularly verify the integrity of your event store data. This might involve checksums or other validation mechanisms provided by your event store tool. Replay capabilities for debugging auditing. Beyond cold replaying for rebuilding projections, ensure you have tooling that allows you to replay specific segments of an event stream to understand behavior, debug issues, or conduct forensic analysis. Disaster recovery plan. Have a clear, tested disaster recovery plan for your event store and associated services. This includes procedures for switching over to a replica in a different region or restoring from backups. Monitoring events, projections, and process managers. Visibility into the health and performance of your event source system is crucial. Event store metrics. Monitor the event store itself. Append rate. How many events per second are being written? Read rate. How many events per second are being read for rehydration projections? Disk I/O, latency and throughput. CPU memory usage for the event store process. Storage growth. How fast is your event log growing? Connection latency. Latency between your application and the event store. Event processing latency. Command latency. Time taken from command reception to successful event persistence. Projection latency. Time taken from an event being persisted to it being reflected in the relevant read models. This is a key metric for eventual consistency. Saga progress. Track the state of long-running sagas to identify stalemates or failures. Event handler projection metrics. Lag. How many events are behind the current head of the stream for each projection handler? This indicates how fresh the read model is. Error rate. How many events are failing to process for each handler? Processing rate throughput. How many events per second are being processed by each handler? Infrastructure monitoring. Standard infrastructure monitoring for your application instances: CPU, memory, network, disk. Distributed tracing. Use distributed tracing tools, e.g., OpenTelemetry, Jaeger, Zipkin, to connect commands, events, and their processing across different services. This is invaluable for debugging and understanding the flow of transactions in a distributed, asynchronous system. Custom dashboards. Build dashboards that visualize key metrics and trends in your event source system, providing a holistic view of its health. Auditing and compliance with event streams. One of the largest benefits of event sourcing is the inherent audit trail. The event stream is the comprehensive, immutable record of everything that has ever happened in your system. Non-repudiation. Because events are immutable and time-stamped, they provide a strong basis for non-repudiation. You know precisely what happened and when. Forensic analysis. In case of security breaches, data corruption, or business disputes, the event stream allows for detailed forensic analysis, letting you replay the exact sequence of actions that led to a particular state or outcome. Compliance. Many regulatory requirements, e.g., GDPR, CCPA, HIPAA, SOX, financial regulations, demand detailed audit trails. Event sourcing simplifies meeting these requirements significantly. You can often generate compliance reports directly from the event stream. Data retention. While event sourcing provides data immutability, data retention policies still apply. You might need to consider strategies for archiving very old events, or for processing right-to-be-forgotten requests, which are complex for immutable logs and often involve data masking or re-encryption strategies, rather than true deletion. Metadata in events. Ensure that important metadata is included in your events, e.g., actorid for who initiated the change, correlationid for tracing, timestamp for when it happened. This metadata is crucial for effective auditing. Going live with an event source system is a journey that requires continuous operational vigilance and refinement. The paradigm shift from mutable state to immutable event streams offers significant advantages in terms of auditability, recovery, and scalability. But it also necessitates a new approach to deployment, monitoring, and problem-solving. By embracing these best practices, you can ensure your event-sourced application runs smoothly and reliably in production, delivering on its promises of resilience and insight. In our final chapter, we'll look forward, exploring the future trends and implications of event-driven architectures. 14. The future of event-driven architectures and event sourcing. We've journeyed from the foundational concepts of event sourcing and domain-driven design through their practical application in building resilient, scalable systems. But the landscape of software engineering is constantly evolving. In this final chapter, we'll briefly look at how event sourcing fits into the broader event-driven ecosystem, touch upon emerging trends and tools, and offer some concluding thoughts on its place in modern software development. Serverless functions and event sourcing. The rise of serverless computing, e.g., AWS Lambda, Azure Functions, Google Cloud Functions, presents a compelling paradigm for implementing event-driven architectures. Serverless functions are inherently reactive, designed to execute code in response to specific events. Function as an event handler. Each serverless function can act as a lightweight, independent event handler. When a new event is appended to your event store or published to a Kafka topic, it can trigger a serverless function that builds a projection, updates another service, or initiates a process. Cost efficiency. You only pay for the compute time your functions consume, which can be highly cost-effective for event-driven workloads, especially those with intermittent or bursty traffic. Scalability. Serverless platforms automatically scale functions up and down based on demand, abstracting away much of the operational burden. Simplified deployment. Deploying a projection builder or a microservice that reacts to events becomes as simple as deploying a serverless function. Challenges: cold starts. Initial invocation of a function can suffer from cold start latency. State management. Serverless functions are typically stateless between invocations, requiring careful design if a function needs to track state across multiple events, though this is where the event store or Saga state can shine. Debugging. Distributed debugging across many small, ephemeral functions can be complex. Despite these challenges, serverless functions can be a powerful complement to event sourcing, allowing for highly flexible, cost-effective, and scalable event consumption patterns. Emerging patterns and tools. The event-driven ecosystem is vibrant, with continuous innovation. Event mesh. As the number of services and events grows, managing event routing and discovery becomes complex. An event mesh provides a dynamic network that manages the flow of events across distributed applications and environments. It enables events to publish and subscribe to any application, regardless of where those applications are deployed. Stream processing frameworks. Tools like Apache Flink, Apache Kafka Streams, or KSQLDB are becoming increasingly popular for rich, real-time stream processing capabilities. These frameworks allow for complex aggregations, transformations, and analytics on events as they happen, before they even hit a read model. This can enable real-time dashboards, fraud detection, or dynamic pricing based on a live stream of business events. Event-native databases. Beyond specialized event stores, some databases are beginning to incorporate event-driven features more deeply, such as change data capture, CDC mechanisms that can push database changes as events, or built-in capabilities for event streams. Low-code, no-code event orchestration. Platforms are emerging that simplify the visual orchestration of event flows, making it easier for non-developers or citizen developers to design and implement event-driven business processes. Advancements in event store technology. Dedicated event store solutions continue to evolve, offering improved performance, easier deployment, e.g., managed services, and richer query capabilities directly on the event stream. These advancements underscore a broader industry trend towards embracing events as a fundamental building block of modern distributed systems. The broader landscape of event-driven systems. Event sourcing is a specific pattern within the much broader category of event-driven architectures, EDA. While event sourcing focuses on persisting transactional state as an immutable log of events, EDAs encompass any system where components communicate primarily by publishing and subscribing to events. Other common EDA patterns include publish-subscribe, pub-sub, the most basic form where a publisher sends messages to a topic and subscribers receive them. Event sourcing often uses pub-sub for publishing its events to downstream consumers. Change data capture, CDC, capturing changes from a traditional database, e.g., SQL Server's change tracking, Debezium for Kafka, and publishing them as events. This is sometimes used as a migration path or a complementary strategy to event sourcing for systems that don't fully adopt it. Event stream processing. As mentioned above, continuously processing streams of events for real-time analytics or to derive new events. Event sourcing often forms the transactional core of an EDA, providing the definitive, immutable source of truth for changes. The events produced by an event source system then feed the rest of the EDA, allowing for flexible reaction, integration, and analysis across the entire enterprise. Final thoughts and next steps for the reader. Event sourcing is not a panacea, nor is it a simple drop-in replacement for traditional data management. It fundamentally alters how you think about data, state, and system design. It introduces a learning curve and new complexities, particularly around eventual consistency and event versioning. However, for systems that demand deep auditability and historical insight, high scalability and resilience, the ability to adapt to complex, evolving business processes, loose coupling between highly autonomous services, event sourcing offers unparalleled advantages. It encourages a deeper understanding of your domain, leads to systems that mirror business processes more accurately, and provides a powerful foundation for building truly event-driven, adaptable software. Your next steps: start small, don't try to event source your entire system at once. Pick a well-defined bounded context or a small, relatively isolated feature. Focus on domain modeling. Reiterate and practice domain-driven design principles. Get comfortable with the ubiquitous language, aggregates, and identifying meaningful domain events. Event storming is an excellent starting point. Experiment with tools. Get hands-on with a dedicated event store, like EventStoreDB, and explore how to build simple projections and command handlers. Embrace incremental adoption. Many systems benefit from a hybrid approach, using event sourcing for core, high-value contexts while retaining traditional CRUD for simpler, less critical parts. Continue learning. The world of event-driven architectures is vast. Explore message brokers, Kafka, RabbitMQ, different NoSQL databases for read models, and stream processing technologies. By now, you should possess a comprehensive understanding of event sourcing, its core patterns, and its synergistic relationship with domain-driven design. You are equipped not just with the what and the how, but crucially, the why. Armed with this knowledge, you are ready to embark on your own journey of designing powerful, resilient, and insightful systems by designing with events.